Okay, so this is the second lecture of the problem solving session. And as the first example, I want to show you this one. Here you will see two different graphs. In the first one, we have a horizontal tangent, while in the second one, there is no, in the first one, we have a vertical tangent, and in the second one, there is no vertical tangent line at the origin. Why it happens like that? If you start drawing tangent lines to this graph, starting from here, you see that they are getting more and more vertical towards origin. Also from the other side, if you do the drawings again, the tangent lines, they move like towards the vertical line and they match at the origin. That's why you can draw a vertical tangent line at the origin to the first graph. What happens in the second graph? If you start drawing tangent lines like this on the left, their slopes are getting really close to minus infinity towards origin, and on the right side the slopes are getting bigger and at origin you have plus infinity slope. So since this time the tangent lines do not match, that's why we say that there is no vertical tangent line at origin, because on one side slope is minus infinite, on the other side slope is plus infinite. Okay, now let's also discuss the differentiability of the functions. If even you don't have the graph here, by using the differentiation rules, you can find out whether this function is differentiable at origin or not. Okay, let's take the power down, subtract 1 from the power, right? And if you rewrite this part like this, the first derivative function is given like that. And as you can see, this function is not defined at the origin. You cannot insert zero to the denominator, right? So this function is not defined at the origin. So it is, since this is the first derivative function and it is not defined, our original function, you say, is not differentiable at origin. And this is a very nice example showing you that even if your function is not differentiable at some point, you may still have a vertical tangent there. But in the second one, your function is not differentiable, and also there is no vertical tangent line because of this minus infinity plus infinity slopes at one side and the other side of the infinity. Okay, let me also show you why it is not differentiable by taking the first derivative of it algebraically. So similarly, you take the power down, you subtract 1 from the power, minus 1/3. So it is 1/3 times x to the power 1/3. And as you can see, first derivative, this value is not defined because you cannot put 0 to the denominator. So g of x is not differentiable at x equals 0. Okay, two different examples. I wanted to emphasize these two examples for you. They both not differentiable at origin, but the difference is that the first one has a vertical tangent while the second one do not have a tangent at origin. Okay? So let me move on. If no questions, we solve this one now. We will talk about derivative as a function. Okay, for example, for the exercise 9, we want to compute the first derivative as a function by using the limit definition. Okay, this is another notation for the first derivative. You can also write it like this. Our function s depends on t. So the limit definition for the first derivative goes like that. S t plus h minus s of t divided by h. If you insert this explicit expression for the images here, what is this, for example? It is, instead of t, we have t plus h. T plus h divided by 2 times t plus h, again plus 1. What is this? It is the function itself, right? T plus h, sorry, there is no h anymore. It is just s of t, t over 2t plus 1, for example. And then you will take this difference by writing over a common denominator. If you do all the computations, at the end, you will find something depending on on which variable? Depending on t. This time, the independent variable is t, and that result will be the first derivative function for you. So I leave this computation to you, okay? So let me move on with any questions. Can you complete the computation here? All you need to do is to write this over a common denominator, do all the products, and you will start getting simplifications and so on. Okay? And the result will depend on t. That t-dependent value will be the first derivative function for you. Okay, if no questions, I want to move on. This time, what we want to find? We want to find an equation of the tangent line at the indicated point. Let's do that. To construct the equation of the tangent line, we first need the slope of it at the given point, right? Slope of the tangent line at x equals 6. Okay, what is that? It is the first derivative of function evaluated at 6. So the limit definition goes like that. f6 plus h minus f of 6 divided by h. Okay, let's write down the images now by using this explicit definition. 8 over square root x minus 2, instead of x, we will write 6 plus h. So what we need to write there is limit h goes to 0, 8 over square root of 6 plus h minus 2 minus f of 6. What is that? It is 8 over 6 minus 2, right? I am just using the explicit formula given to compute the images like this, divided by h, okay? Then what we have, limit as h goes to 0, here we have 8 over, what is this, square root 4 plus h, minus, what is this value? By the way, I am sorry, this should be not 4 but 2. You should warn me on such mistakes, okay? Then this is just 4 divided by 8, and next, limit as h goes to 0, we can write it over a common denominator like this. Okay, let me just, sorry. 8 minus 4 times the denominator. Then divided by 8 times this. Okay, then if you insert h goes to 0, what you have? You will have 0 over 0, which is an indeterminate form. How we get rid of such indeterminate forms while computing limits? We will multiply and divide by the conjugate of that expression, right? 8 plus, this is the conjugate, like that, 8 plus 4 times this. Now we have a minus b, a plus b form. That's why I can multiply it. I can do the product quickly. A square is 64 minus b square. Square of this second expression is 16 times 4 plus 8, and denominator is this whole thing, okay? 8 times 4 plus 8 square root times 8 plus 4 plus 8 squared. Okay, like that. Now, if you do this product, you will have simplification like that. And what you obtain is minus 16h. And then these h's will also be simplified. Then you can just insert h equals 0 to see the result. You have minus 16 at the denominator. At the denominator, you have square root 4. I am just, sorry, we'll write infinity here. H goes to 0. So send all the h's to 0. Square root 4 times, what about this part? 8 plus 8, 16, I guess. So the result is minus 1/2. This is the first derivative evaluated at 6. So it is in fact the slope of the tangent line. Now I am ready to construct the equation of the tangent line, okay? Let's construct. Okay, so equation of the tangent line now. Tangent line is, we know the slope. Slope is computed here by this limit definition of the first derivative. Slope is the first derivative at 6 and it is computed as -1/2. Second, we also know the point. What is the point? 6, 4. It is given in the statement. Then you use your famous equation of tangent line formula like that, m times x minus x0. So it goes like y minus 4 minus 1/2 x minus 6, right? These are x0, y0, and the slope inserted. Okay, this is the equation of your tangent line. Any questions? Okay, no questions. I can move on. Now, over this graph, we will detect the points at which your function is not differentiable. Okay, we want to find the points where the first derivative is not defined. I think I can make a quick recall here about at what points the graph fails to have the first derivative. Let's recall it. I covered it in my recorded lecture video, but let's recall. If you have corners like that, or cusps, or wild oscillation behavior. Remember, we solved the wild oscillation function in the first part. And what may happen? If you may have some jumps, or if you have some defined points like this, then at such points, at all those points, here, here, at the wild oscillation point, here, here, and here, your function is not differentiable, okay? This is a corner. This is a cusp. Here we have a wild oscillation. And here there is a jump in your graph, also another jump. So for these two, your function is not continuous because you break the graph. That's why it is not differentiable. And for these two, your function is continuous but not differentiable, okay? Here and here, not differentiable again. And here, at the wild oscillation point, not continuous and not differentiable. But if you suppress or if you compress, let's say compress this wild oscillation, push it to have a unique value, your function may be continuous there. But here it is not compressed. We didn't push it to squeeze like to approach one point, so it is not continuous in my graph here. Okay, for such cases, your graph fails to have first derivative. So let's look at this graph again. At this point, and here, we have corners, right? These are corners at the graph. So at those points, your function is not differentiable, right? Because of the corner. Not differentiable. But is there any problem about continuity of this graph? Is there any breaks, jumps, holes? No. So this graph continues everywhere, but there are some problems about differentiability at these 3 points, okay? Can I move on? Let's move on. Again, we have a piecewise defined function. We want to understand whether this function is differentiable at the origin or not. So to check differentiability, what do we do first? We check first continuity, right? This is what you should do to check differentiability. You need to check first continuity at the given point, of course. Continuity at x equals 0 at origin. Okay, how do we check that? We look at one-sided limits, right? F of x, x goes to 0 from right. we need to check whether the one-sided limits are equal or not. If they are the same, limit exists. If the limiting point is the same as the image of the function at origin, then you can conclude that it is continuous. But let's check first one-sided limits. If x approaches 0 from right, so x is greater than 0, so we need to use this definition. If x approaches 0 from left, then x is less than 0, you need to use this definition. Plus 2x plus 7. Okay, now we are ready to compute the limits. If x goes to 0, the limit on the left is minus 1. If x goes to 0, the limit on the right is what? Is 7. And as you can see, they are different. Since one-sided limits are not the same, we conclude that the limit of this function at origin, this limit does not exist. If there is no limit, your function is not continuous. F of x is not continuous at x equals 0. If your function is not continuous, what do you conclude about differentiability? What do you say? Then, if not continuous, automatically not differentiable. Don't forget this. This is a theorem. If your function fails to be continuous, then you can directly conclude that your function is not differentiable at x equals 0, okay? Not continuity implies not differentiability. This is a theorem. So that's it. Your function is not differentiable at the origin because it is not continuous. If your function is not continuous, you cannot talk about differentiability. It is directly not differentiable. Can I move on? Any questions?
No, teacher.
Is everything clear? Okay, let's move on. This time, again, this is a geometrical question. By looking at the graphs, we will decide the points at which it is differentiable, it is continuous but not differentiable, and neither continuous nor differentiable. Let's analyze the graphs. Look at the first graph. We draw it without lifting the hand, right? So there is no problem about continuity because there is no jumps, there is no breaks, there is no holes. We just draw it without lifting the hand like that. So this line is a perfect example of a continuous function everywhere. So this graph is continuous everywhere. What about differentiability? Is it differentiable over its domain, over this given domain? What do you think? Is there any corners, any cusps, any wild oscillations, any breaks on this graph?
No.
No. That's why you can conclude that this function is also differentiable over the given domain. I won't write everywhere on D. Over its domain, it is also differentiable. There is no problem about continuity and differentiability, right? Let's look at the second one. I start drawing the graph like this, and I, again, didn't lift my hand so that there is no jumps, breaks, holes on this graph. Also, there are no corners like this. There are no cusps like this. There are no wild oscillations. There are no breaks like this. So, since none of them happens, this function is also differentiable everywhere. So, continuous over the given domain, checked, and it is also differentiable as it doesn't contain any corners, cusps, wild oscillations, and so on, right? Okay? Second graph is also continuous and differentiable over the given domain. Okay, let's move on. This graph, except the origin, it seems like there is no problem. Continuous, differentiable, continuous, differentiable. But at the origin, what do you see? There is a jump.
Jump? Yes.
Exactly, there is a jump at the graph. So this function cannot be continuous at the origin, not continuous at x equals 0, right? Can it be differentiable? If not continuous, directly not differentiable at x equals 0. That's it. Okay, look at the next one. Starting from here, you see I draw without lifting my hand. So there is no problem about continuity. But at this point, what do we have? We
Corner.
have corner, thank you. If there is a corner, then your function is not differentiable there. But is it continuous here?
Yes.
Yes. There is no problem about continuity. There is no jumps, breaks at the graph. So it is continuous, but not differentiable at this point. What about this one? Your graph suddenly jumps like this. There is a jump. So here it is obviously not continuous. As it is not continuous, directly not differentiable. And what about here? There is like jump discontinuity here. I mean, removable discontinuity, but it is discontinuous, not continuous, directly not differentiable at the point 2. Okay? So let's move on. Look at this one. I start drawing the graph. Any problem with continuity? This graph is continuous over its domain. But I think there is a problem here about differentiability. What is this point? It is a cusp. At the cusp points, your function is not differentiable. So at this point here, your function is continuous, but not differentiable there. Okay, like that. And the same situation happens with this graph. There is no problem about continuity. This graph is continuous everywhere, but at those 2 points, here and here, these are cusps again. Cusps. So at the cusp points, your function is continuous. Here, your function is continuous, no problem, but not differentiable because there is a cusp there. Okay? So you can detect discontinuity and not differentiable points like this by looking at the graph. Can I move on? Any questions?
Yes, hocam.
Okay, let's move on. I will skip this exercise because we have very limited time here. So try it by yourself. Okay, this is a very nice exercise for you. And finally, we arrived at differentiation rules. From this point on, we are allowed to use the differentiation rules. Up to this point, what we were doing while we want to compute the first derivative function, we were using the limit definition, right? Because I haven't introduced the differentiation rules yet. We were using the limit definition to find the first derivative. But now, I mean, I already introduced the differentiation rules in the recorded lecture videos. Let me remind you. Recall. The simplest rule for the differentiation is the derivative of a constant number. So let's say we want to take the derivative of, sorry, I couldn't write constant. So what is the derivative of a constant real number? It is 0. So next thing is the derivative of the power rule. You take the power down and you subtract 1 from the power, okay? All those rules can be proved by using the limit definition, by the way. I mean, they are proved by using the limit definition, but from now on, you can use them as a rule. Okay, what about the derivation rule for the exponential function? It is itself. They are all explained in the recorded lecture videos. And we also have product rule and quotient rule. Let's also cover them. What happens if you want to take the derivative of a product function? You cannot distribute first derivative directly to the product like this. No, this is wrong. Instead, there is a very special form that you should apply here. Okay, the product rule is applied like this. Derivative of the first function times the second plus first function stays the same, derivative of the second function. This rule is called the product rule of the derivative. Product rule, we will be using this a lot. Don't forget this rule. There is also the similar quotient rule. You cannot directly distribute the derivative to the quotients like this. This is also wrong. Instead, you will be applying this rule. F prime g minus fg prime divided by the square of the denominator. And this rule is called as the quotient rule. Okay, the product rule and the quotient rule, you have to learn them. You need to know them by heart because we will be applying them a lot. Also, there are these kind of differentiation rules, constant, power function, exponential function. Let's apply these rules over some examples here. 37, for example, let's try it. Okay, our function y is given as 7th root of x squared minus x to the power a. Okay, then you can rewrite it as a power function, this part, and this is already a power function. By the way, you can apply this rule where the power is any real number. The power doesn't need to be integer, doesn't need to be positive. Any real number, you can apply it. Okay, now I start taking the derivative. I take the power down and I subtract 1 from the power. Similarly, take the power down, subtract 1 from the power. You see, that's how you should apply power rule. Also, let's try 34. Y is given as minus 3 over 5 plus pi, like that. Okay, y prime. You see the power is negative real number, but still you can apply the power rule. The power comes down and you subtract 1 from the power, like this, plus, what is the derivative of this thing? You know, it's a constant real number, right? And the derivative of a constant number is 0. So you will just put 0 here. Okay, what else? Let's apply product rule to solve 40. Here, the function is given as, you know, this function, r. Function depends on theta, and it is given as e to the power theta, 1 over theta squared, theta to the power this, pi over 2. You know, this is a product. That's why we have to apply product rule. Product rule. So derivative of the first function, derivative of the exponential function is itself. So itself. Then you write the second function directly as it is without changing anything. Plus, now, first function stays the same, derivative of the second function. You can write this ratio as a power function like theta to the power minus 2. Then minus 2 comes down while taking the derivative of it, and you subtract 1 from the power, plus, again, power, take the power down, subtract 1 from the power, minus 1. Okay, what I have done here is, let's call this f and this part as g. So this is f prime times g plus f times g prime. This is what we call as the product rule. Okay, let's apply quotient rule now, if no questions. F of s is given as 23. Where is it? Yeah, I choose this one. F of s as given as square root of s minus 1, square root of s plus 1. I need to apply quotient rule. Let me call this function as h of s for some reason. Okay, derivative of denominator. How do you take the derivative of the square root function? Let's put a very quick recall about that. You can quickly take the derivative of square root function with this rule. You have I mean, this is the quick way of doing that. And you can easily understand why it is like this. This is x to the power 1/2. While taking the derivative, you take the power down and you subtract 1 from the power, which is the same as this thing. Okay, derivative of square root of s is 1 over 2 times square root of s. Minus 1 is 0, so derivative of the denominator is this one times the denominator minus. Numerator stays the same, times the derivative of the denominator function like this, divided by the square of the denominator function. So this is the first derivative function computed by applying quotient rule. Okay, so if I call this f and call this g, this is f prime times g minus f times g prime divided by g squared. Okay, so let's move on. Any questions? So we start applying differentiation rules. Next week, we will solve more complicated and advanced differentiation problems. But for this week, I think this is enough. And the last group is about the differentiation rules of trigonometric functions. How many trigonometric functions do we know? Let's put a recall here. Okay, sine x, cosine x. These are the trigonometric functions. Tangent x, cotangent x, secant x, and cosecant x. Now I want to show you the first derivatives of these trigonometric functions, differentiation rules for it. Derivative of sine function is cosine. Derivative of cosine is minus sine x. Derivative of tangent is secant square x. Cotangent similarly cosecant square with a minus. Derivative of secant is secant times tangent x. Cosecant similarly cosecant x times cotangent x with a minus sign in front. Okay, let me give you a hint how to remember these rules. All the trigonometric functions starting with co has this minus sign in its first differentiation rule, okay? And the rest you need to learn. Okay, let's solve 1 or 2 examples from this group, then I will stop. Let's solve 7. F of x is given as sine x times tangent x, and I want to compute the first derivative. Obviously, I will apply product rule because this is a product function. So derivative of sine x is cosine x times the second function plus first function stays the same as sine x times the derivative of the second function. What is the derivative of tangent? It is secant square x, right? Okay, this is derivative of sine and this is derivative of tangent. Okay, let's deal with 9 here. Y function is given as secant x plus tangent x, secant x minus tangent x. Like this. Okay, let's try to solve the first derivative. Again, we need to apply product rule. Derivative of this first function goes like derivative of secant is secant x times tangent x plus derivative of tangent is secant square x, right? Okay, derivative of tangent is secant square x. Okay, this is the derivative of the first function times the second function. You don't touch the second function. Plus, now plus. Now I will write the first function as it is without touching it. This is the first function, secant plus tangent x times now derivative of the second function. Secant is derivated as secant x times tangent x minus secant square x. Okay, like that. Maybe we can also solve 4 and then I will stop. This is the last exercise. Square root of x times secant x plus 3. Okay. Be careful about the products. You need to apply product rule. Derivative of the square root function is 1 over 2 times square root x times the second function plus. You see, I'm applying product rule plus First function stays the same times the derivative of the second function, which is secant x times tangent x, and then plus what is the derivative of 3? It is a constant number, so its derivative is 0. So this comes from the derivative of square root of x, and this comes from the derivative of secant x while we were applying the product rule. Okay, any questions? Let me indicate that we applied product rule here, also here. Product rule also here. Okay, if no questions, I want to stop here. Okay, and stop.